Hello again to another Agakala Reacts, and today we'll be watching the weird way we measured an entire universe from Be Smart. And from the corner, I can see it's another PBS video. We just made a reaction to PBS Eon yesterday. So let's just see how do we measure and why is it weird for the universe measurements.
Hey smart people, Joe here. How do we figure out how far away things are? If you're measuring the distance to an object nearby, it's pretty easy. We take another object whose length that we know, and we use it as a reference to find that distance. What about an object that's beyond our physical reach? Well, we can literally walk to that object and count our steps to calculate the distance. Even something as far away as the moon, we can shine a beam of light, bounce it off special mirrors left on the lunar surface by Apollo astronauts, count how long that light takes to make the round trip, and calculate distance. These are all ways of measuring using things, physical objects in the world around us. But how do we measure how big?
Is it then that we didn't know how far exactly the moon is before they actually land on the moon? We must have known that, didn't they? There was some kind of
Universes. This is a video about the tools we use to answer that question. Since the time of the ancient Greeks, scientists have been constructing a cosmic measuring tape to measure the universe from our own backyard all the way to its ever-expanding edge, the cosmic distance ladder. Let's climb it and learn our true place in space. The first ancient skywatchers knew that our moon, the planets, and the stars were incredibly far away. And before they had the technology to even try measuring these distances precisely, early astronomers in ancient Greece figured out one cool trick based on basic geometry that would become the key to measuring thousands of distances in our own galaxy. It's called parallax. Parallax is why when you look out the window of a moving car, things closer to you, like trees, seem to move more than faraway mountains, and things that are super far away don't appear to move at all. It's also why when you look at something right in front of you and then close one eye, then the other, the distance between your eyes makes the object appear in a different place against the background. Chances are many of you are doing this right now, holding
I was
something
just going
up
to
and opening
do
one
that
eye
too.
and then the other. That's parallax. The key is, the closer an object is, the more its position seems to change as you look at it from a different perspective. Astronomers use this same trick to measure distances to planets and stars by looking at things with two different eyes. Only the eyes they use are thousands of miles apart. Way back in the 2nd century BC, the Greek astronomer Hipparchus used this exact trick to figure the distance to the moon. He compared observations of a solar eclipse from two separate locations. At one location, people saw a total eclipse, and the other saw 4/5 of the sun covered. Hipparchus knew the distance between the two locations, his two eyes, and the angle that the moon appeared to move. So he could calculate the distance to the moon with some basic geometry.
That's some
And in
smart thinking there.
1672, Giovanni Cassini used the same trick to calculate the distance to Mars. What's amazing is Hipparchus and Cassini were both really close to the actual distances we know today, without any of our newfangled modern technology. Parallax is a great way to measure distances to objects in our solar system, but we can even pick up the parallax of some stars. To do this, astronomers use Earth's position at different times of year as two different eyes. By looking at a closer star several months apart, they can measure how the background stars appear to move, do a little math, and calculate distances. A satellite named after Hipparchus used super precise angular measurements to map the distances to some 2.5 million stars. But parallax only works up to a certain distance. To go deeper into the universe, we need to add another rung to the ladder. By the 1920s, astronomers had a pretty decent map of our galaxy. The distances weren't spot on, but the spiral arms were there, the nearby objects were in place, and astronomers had a rough idea of how big our galaxy was. The numbers were so huge, we stopped measuring in terms of distance and started measuring in terms of time, how long it would take light to travel that far. But as this vast picture was coming together, there was a hint that there might be way more to the universe than anyone had imagined. In the 19th century, astronomers had started noticing mysterious fuzzy objects they called spiral nebula. Some people thought these were just gas clouds within the Milky Way, but others believed they were so-called island universes, whole galaxies outside our own. And this was a huge debate among astronomers. Could there really be galaxies besides ours? On the night of October 5th, 1923, astronomer Edwin Hubble aimed a 100-inch telescope toward a mysterious fuzzy spot in the sky and captured a photograph. As he pored over the image, comparing it to others from different nights, he noticed one little speck was changing over time, gradually brightening and then dimming. This was exactly what he was looking for, a slowly blinking star called a Cepheid variable. Years earlier, astronomers had learned that the brightness of these stars, along with how fast they pulse, could tell us how far away they are. The astronomer Henrietta Leavitt had figured out the relationship between a Cepheid's pulsing and its true brightness. For instance, a star that takes 30 days to go through one cycle of light and dim is going to be bright, around 10,000 times brighter than our sun. Meanwhile, a star that goes through one cycle every day or so is going to be on the dimmer side, only a few hundred times as bright as the sun. If you know how fast a Cepheid star blinks, now you know how bright it actually is. But depending on how far away it is, that blinking star will appear dimmer. So when we measure how much it dims when we actually look at it, we can calculate the distance to that star. Objects like this are called standard candles. They're lights that we know how bright they actually are so that we can reveal the distances between us and them. Doing that would require a new rung on our cosmic distance measuring ladder. And for this one, we need to split light into a rainbow. If you look at any star's light like this, you'll find that a bunch of lines are missing. Much like a barcode, these missing lines are a fingerprint of the elements that star is made of. But astronomers noticed that the lines in these barcodes weren't always showing up at the wavelengths that they expected.
Okay.
Sometimes they were shifted towards the blue end of the spectrum and sometimes towards the red.
That's so cool,
They
though.
realized that they were looking at a weird but familiar phenomenon, the Doppler effect. This is an effect that happens when something that's emitting waves is also moving relative to the observer. You've almost certainly experienced the Doppler effect here on Earth. But astronomers can also use it to map our universe. In 1912, an astronomer named Vestos Slipher started using spectroscopy to study those mysterious spiral nebula, the ones that turned out to be other galaxies. And he noticed that most of their color fingerprints were extremely shifted to the red side, or redshifted, meaning these things were moving away from us at unbelievable speeds too. We're talking hundreds of kilometers a second. Then, in 1929, Hubble realized something even more mind-blowing. The farthest galaxies seemed to be moving away the fastest. That could only mean one thing. The universe was expanding. Suddenly, the picture of the universe that astronomers have been after for so long wasn't a picture after all. It was a movie. But that raised another new question. Just how
question
fast
after
was
question.
it expanding? And what did this mean for the fate of the universe? To answer that, astronomers would need to peer even deeper into space, and they'd need to add yet another rung to our cosmic distance ladder. The key to these questions were supernova. Powerful explosions of massive dying stars that for a short instant flash as bright as an entire
That
galaxy.
is very bright.
A certain supernova called
Wow.
Type 1As all max out at a similar brightness, which means whenever one goes off, we can use it as a standard candle, just like Cepheids. But since supernovae are so bright, we can detect these standard candles halfway across the visible universe. And that lets us take one more big step on the cosmic distance ladder. By the 1990s, astronomers had used this ladder to put together a detailed picture of an unthinkably vast universe, one that seemed to be expanding as far as the eye could see. When astronomers looked at light from the most distant supernova they could see, they found something completely surprising, something that didn't fit any of their previous ideas. The expansion of the universe was not slowing down, not even a little. It was accelerating. What was pulling our universe apart? And how had this tug of war between gravity and whatever this mysterious expanding force is shaped the universe over time? Once again, climbing the highest rung of the cosmic distance ladder had uncovered previously unthinkable questions and opened up entire areas of research that didn't exist before. Today, Over 2,000 years have passed since Hipparchus first measured the distance to the moon. Our view of the universe has gone from this to this. We've figured out that the universe has way more than one galaxy, that the edge of the observable universe is billions of light years away, and that our universe is not a photograph, but rather a movie playing out over time. But perhaps most importantly, we've learned that sometimes the most fundamental questions, like how far away is that thing, can lead to surprising new questions that transform the way we see the world. Stay curious. Oh, hey, thanks for sticking around to the end of the video. I've got a really cool announcement to share with you guys. I am hosting a game show. It's called High School Quiz Show. It features some of the smartest high schoolers in the country going head to head to see who knows the most. Making this show is a blast. If you want to see how your know-how stacks up, definitely head over to the High School Quiz Show YouTube channel to watch this year's tournament. It is a doozy. There's a link down in the description, or you can click right up there. And as always, thank you to everyone who supports the show on Patreon. You make this possible. We recently just launched some new levels to support the show and some new perks. So head on over to our Patreon page and you can see a bunch of the cool stuff that we're gonna be sharing in the next weeks and months and, however long we do this thing. Thanks again, and I'll see you in the next episode. Because you couldn't both see Mars if you were on opposite sides of the globe. That's how the sky works. It is a doozy because it's still going on. Astronomer? Astonishing. The astronomer Henrietta, I love it.
Yeah, so if you like this video and you wanna subscribe to them, there's information below. In my description box there's a link to the channel and there's a link to the original video as well. So obviously go and do it. And as always, that was really cool. They kind of explained everything. I kind of understood what they were talking about. Now I have no clue what was going on. So yes, so physics, it's not my thing to do, nor astronomy. And but I do like to watch stuff about it. I think whenever I watch videos like that, I retain like maybe 5% of the information, because this is cool about how they actually how they got how far the moon is 2,000 years ago. That was really great. And yeah, so as always, really interesting video. And yeah, thank you very much for watching. I see you tomorrow. Bye.